Hey everyone, welcome to the next video for section 7.8. So in this video we're going to start tackling the what do we do if we have a repeated eigenvalue but not enough eigenvectors. So we're just going to basically do this through examples. So I'm going to have two examples, one where we have enough eigenvectors to cover everything, and you'll see how that works, and the second where we have not enough eigenvectors and have to work through what happens there. So let's go ahead and just jump right into these examples and showing you how we handle this situation. So repeated eigenvalues. So example one, and for these guys, I'm just going to put the matrix down because the matrix is sort of equivalent to the ODE problem itself. So we're basically just looking for eigenvalues and eigenvectors of it in order to be able to solve an ODE, and then we'll work it all together in general solutions at the end. So the first thing I want to look at is this matrix. A is just 3, 0, 0, 3. All right, so let's look for eigenvalues. And how do we do that? We take the determinant of 3 minus r, 0, 0, 3 minus r, which is just 3 minus r squared equals 0. So this is a double root at r equals 3. All right, so now let's try to find eigenvectors for r equals 3 and see what happens. So eigenvectors, this means I want to look at the matrix 3 minus 3, 0, 0, 3 minus 3 times x1, x2 equals 0. Well, this just is 0, and this is 0. So this just tells me 0 equals 0, 0 equals 0. It doesn't depend on x1, x2 at all. What that means that I have no conditions on x1 or x2. So I can pick pretty much any two vectors I want, and they will be any vector I want will be an eigenvector for this matrix. So I can say then the vectors 1, 0 and 0, 1 are both eigenvectors of A with eigenvalue 3. Now I have here two eigenvectors for my matrix with the same eigenvalue. Now what that means, I can now just write that interlinear into a general solution because I have two different eigenvectors here. So in this case, so for the problem, x prime equals a times x, where a is that matrix up there, the general solution is x of t equals c1 times 1, 0 e to the 3t plus c2 times 0, 1 e to the 3t. And since I had two eigenvectors for this eigenvalue, we are all set. I got myself two solutions. You can prove they're independent. It's not too hard to do that, but I'm not going to do it here. You can take the Wronski and show it's non-zero. It's fine. But this gives me two solutions. This gives me a full set of solutions for here. I didn't have to do anything crazy with this because I had enough eigenvectors to meet the algebraic multiplicity of here. Because the algebraic multiplicity was 2, and I found two eigenvectors for it. Two different eigenvectors for it. So since it was able to do that, I didn't have to do anything fancy and could just find my general solution like that. All right, now obviously not all problems are that easy. So let's take a look at example 2 where it's not going to be that easy. So example 2, we're going to look at the matrix 3, 1, 0, 3. Almost the same matrix, just a 1 instead of a 0. Well, how much difference can that make? Turns out it makes a lot of a difference. So let's look for eigenvalues. Determinant of 3 minus r, 1, 0, 3 minus r. Turns out this is again just 3 minus r squared equals 0, so a double root at r equals 3. And now we look for eigenvectors. And our goal is to find 2. If we can find 2, we're good. However, we'll see we actually can't find 2 here. Because now if I look at this matrix, I have 3 minus 3, 1, 0, 3 minus 3 times x1, x2 equals 0. This tells me that x2 equals 0 and 0 equals 0. These equations, this is 0, this is 0, just become x2 equals 0 x, and 0 equals 0. So I can pick x1, I can pick x1 to be 1. So 1, 0 is an eigenvector of A with eigenvalue 3, but that's all I can find. The only other vectors that will be eigenvectors are multiples of 1, 0, and that doesn't give me different solutions, so I don't care about those. So that's it. I'm now in trouble here because we have an algebraic multiplicity of 2, but I can only find one eigenvector. So we need to hunt for a different solution. So what I know right now, so x1 of t equals c1 times 1, 0 times e to the 3t is a solution to my problem. But that's only one. I need to find a second one. So how do we do that? Well, in the second order case, we multiplied by t. So why don't we try that again here? So let's look for a solution of the form some vector c times t e to the 3t. Right, so 3 is a double root. So let's try to look for something like t to 3t. So let's put a c random vector in front of that, and we'll see what equation this c has to satisfy to see if we can pick this guy to be our second solution. So let's plug him in. So we're trying to solve this problem, x prime equals ax. We'll just leave a for now. We'll end up putting a in later when we need it. But let's take both sides of the equation. Let's plug in our function up here to both sides and see what we get. So I'm going to let this be x. Then x prime is going to be the vector c times e to the 3t plus 3t e to the 3t. We're taking the derivative of t to the 3t. And then a times x is going to be ac times t e to the 3t. Now I want these two sides to be equal, but this left-hand side here has an e to the 3t term, which doesn't show up over here. So in order for this to work, I need c to be the 0 vector, to make both sides equal. Well, that's not great. That means this will be found, which is a 0 solution, which is not what I want to be looking for anyway. So this wasn't good enough to look for our answer. So instead, we're going to be a little more general, and we're going to add in an e to the 3t term, because maybe that'll cancel out this e to the 3t that we get from taking the derivative of t e to the 3t. So instead, look for x to be c times t e to the 3t plus eta e to the 3t. So the idea here is the same as what you would do for undetermined coefficients when you're guessing stuff for the right-hand side. When you guess t e to the t, you also have to guess e to the t, because in taking derivatives, you produce e to the t's. So here we want to guess a c and an eta, which can be any vector we want in this function here. And now we're going to plug this guy into both sides and see what happens for there. So x prime is going to be c e to the 3t plus 3t e to the 3t, like it was before, plus eta 3 e to the 3t. And ax is going to be ac t e to the 3t plus a eta e to the 3t. Well, now I've got terms on both sides, so let's match them up based on what they have as their functions of t. So if I look at my t e to the 3t term, what I see on the left is 3c, and what I see on the right is ac. And for e to the 3t, what I see on the left is c plus 3 eta, and on the right I see a of eta. Now this first equation is something we already know. This says that c must be an eigenvector of eigenvalue 3. But I know one. This is what we did for the first part of this problem. So c is the vector 1, 0. And now I can plug this into here to try to solve for eta. So now I want to do that. So eta is going to be a vector that is eta 1, eta 2, and we're going to plug this in. So c is 1, 0. 3 eta is the vector 3 eta 1, 3 eta 2, equals a, which is 3, 1, 0, 3, times eta 1, eta 2. So on this side I have 1 plus 3 eta 1, 3 eta 2, equals 3 eta 1 plus eta 2, 3 eta 2. And if you write this out as a linear system and you can cancel things on both sides, what you'll end up seeing is this tells me that eta 2 has to be 1. It gives me no condition on eta 1, but I might as well set it to be 0 because I know that 1, 0 already satisfies my equation, so I can just pick 0 and be fine. So the vector I want here is I want eta to now be the vector 0, 1. And that will solve my problem. So what I get as my second solution is x2 of t equals some constant c2 times c, which is 1, 0, t e to the 3t, plus 0, 1, e to the 3t. So then finally, after all that, I get my general solution, which is x of t equals c1 times 1, 0, e to the 3t, plus c2 times 1, 0, t e to the 3t, plus 0, 1, e to the 3t. And you could again show, just like we did in the repeated root case for second order equations, that these two are independent and they both solve your equation, so you're good to go. So recapping how this process worked, we found eigenvalues, so we had a double root. We then looked for eigenvectors and saw we only had one eigenvector, which means we had to look for a second solution. The guess we needed, it turned out, was c t to the 3t plus eta e to the 3t. You plug it in, you solve it out, you see that the c had to be your original eigenvector to begin with. So these two being the same, this 1, 0 and this 1, 0, is always the case. That's not a coincidence there. And then you have to solve for what this guy has to be over here by plugging into the equations. All right, so that's the point I'm making for this video, is just where we get these things and where we get these solutions from. So the next video, we're going to go through getting the phase portrait diagrams for these kinds of things, both in the case where you have all the eigenvectors and in the case where you don't. So we'll look at that in the next video. All right, thanks a lot for watching, and I will see you in that one.